Good evening and welcome to this week's Casio Education webinar. Very pleased you were able to join us tonight. My name is John Deal. I'm serving as the host of this webinar for you. A little bit of information about me here on the screen. And I will be fielding questions and again acting as a moderator. But most importantly, our presenter this evening is Dr. Bob Horton from Clemson University. He's in the Mathematics Education Department with specialties in inquiry-based instruction and the use of instructional technology, including our Casio calculators. And he's going to give you some very interesting demonstrations tonight that kind of combines both of those topics together. We'd like to make one request this evening that our audience will be on mute for most of the time. It just allows us to conduct this webinar with a little bit fewer distractions. However, you are completely welcome to type in any questions you have in the dialog box under the questions, and we promise we will either type an answer to you or we will throw that question to Dr. Bob and have him address it live. One way or another, please feel free to do that. And without any other delay, I am very pleased to turn over our webinar to our presenter, Dr. Bob Horton. Thank you, Bob.
Well, thank you, John. And I see a blank strip down the right side of my screen. I hope it shows up all right on your end over there. As John said, I'm Bob Horton, and I work at Clemson University. Tonight's webinar is on expressions and equations, building toward the abstract and exploring relationships. Often in education, particularly in mathematics, things that seem extremely obvious to some are not at all obvious to others. Frequently, this is because ideas, particularly those that use algebraic symbols, are too abstract for students. One of the many roles that the successful teacher fills is that of one who provides students with the experiences that help develop an understanding of these abstractions so that they become intuitive. And as a mathematics education researcher named Fishbein concluded, what we as teachers should do is to facilitate the development of intuitions so that ideas which were non-intuitive become intuitive. That is, teachers should foster a deep understanding of mathematical concepts that become second nature for students. To develop this intuition, we should build toward the abstract, not build from the abstract. Having a little delay here on my screen, so I'm pausing for a moment here. There we go. Researchers such as Jerome Bruner determined that learning works best when we progress from context to concrete models if possible, to numerical or tabular representations, to graphical and visual models, and finally to the abstract or symbolic. If we begin with the abstract, expressing ideas in symbols, then students are forced to memorize and are likely to forget quickly as they do not own the ideas. Sadly, in a typical math classroom, we begin with abstract ideas and then have students attempt to use these ideas that they have just been exposed to and apply them in complicated situations. This is not to say that complex word problems are not worthwhile. They can serve a worthwhile purpose. What it does suggest, however, is that in the development of ideas, we as educators should begin with simple context that students can understand, develop concrete, numerical, and visual representations of these ideas, and then, and only then, move on to the abstract representations. In this session, we hope to provide some suggestions and strategies that teachers can use to help students make sense of expressions and equations, beginning with context and moving toward the abstractions. Let's begin with a context that all students can relate to. Suppose you're completing an assignment or a test, and you have already obtained 8 points. You'll receive an additional 3 points for each additional correct answer as you continue. Rather than asking a closed-ended question, such as, how many questions will you have to answer correctly in order to achieve a total of 20 points, teachers might use the scenario to have students investigate. After having students rephrase the context in their own words and discussing the meaning, the teacher should encourage students to consider what relationship they might investigate. Even elementary students can quickly identify that they can look at the relationship between the number of questions answered correctly and the total number of points the student will have. After giving students some time to look at different values, students should see the need to organize the results. It's now time to work with the calculator to explore this. From the main menu, select Statistics. We will build a table of values using List 1 for the number of questions we have answered correctly and List 2 for the number of total points we now have. In List 1, we will input the integers from 0 to 6. Students, of course, can do this quite quickly, though it may be worth showing them how to do this with a sequence because we are preparing them to understand expressions. Highlight List 1 and press Options, F1 for List, F5 for Sequence, and input X, comma, X, comma, 0, comma, 6, comma, 1. Close the parentheses. The first X is the expression. For novices, we can simply say use this whenever you want to count. The second X indicates the variable. 0 is the start number, 6 is the end number, and 1 is what we want to count by. If students are curious and ask, then it may be worthwhile to explain more about the sequence command, but it isn't necessary at this point. Press Execute to generate the list. In List 2, students should enter the number of points they will have attained. Students should have little difficulty identifying the correct values. 8, 11, 14, 17, 20, 23, and 26. We can label the lists if we want. In List 1, this was the number of questions that we had answered correctly. And in List 2, we had the total number of points. A couple of simple closed-ended questions at this point can help you assess whether the students have entered the data correctly and understand the table. For example, you might ask, how many points will you have if you answer 3 questions correctly? And they should see that it would be 17. Also, you might ask about the inverse. For example, you might ask, how many questions will you need to answer correctly to attain 26 points? And you can see it's 6 questions would produce 26 points. Here your emphasis is on only the tabular representation of the data. Building and interpreting tables is essential if students are to master the ideas of algebraic expressions and equations that we are building toward. Next, we'll create a graph of the data. But what type of graph should we create? Too often, we as teachers do not identify the variables we're exploring. Here we want students to understand that there are 2 variables of primary interest, both of which are numerical in nature. The number of questions answered correctly and the total number of points attained. However, rather than telling them that, we should have the students determine this on their own. When we have two numerical variables, we typically are interested in XY line plots and scatter plots. Though these graphs are similar, students should recognize that XY line plots play connect the dots, while scatter plots do not. If this is one of the first times our students have conducted an investigation such as this, we may want to suggest that a scatter plot here is more appropriate. For advanced students, we can discuss the implications of connecting the dots. By doing so, we imply that the number of questions we can answer correctly is continuous, that we could get 2.5 questions right, or 5 3/7 questions right, or even for really advanced students, the square root of 3 questions correct. Again, though, for beginners, this is not an appropriate part of the exploration or perhaps even the discussion. We can tell them that a scatter plot is often appropriate to investigate the relationship between two numerical variables. Press Shift-Exit, which is quit, to return to the Home Statistics screen. Select F1 for graph and F6 for set. We want to set up StatGraph 1, although this is the default on the calculator that we want. We want the scatter plot that uses list 1 for our X, list 2 for our Y, and a frequency of 1. Press Exit to leave the graph setting and select F1 for graph 1. Arrowing down can be helpful so we can see the values on the x-axis, although I've lost some of the points. If you're trying this and your graph doesn't look the same as mine, in the statistics setup, I've got the coordinates on, the grid on line, and the axes on scale. I've set the x scale at 1 and the y scale at 3 to try to help reinforce the connection while foreshadowing the algebraic representation we're leading to. Before analyzing the graph, we should trace through the points to ensure that students understand how this graphical representation connects with the tabular representation. Select Shift F1 for trace, and arrow right and left, questioning students about the meaning of the numbers. Here we see with 0 additional correct answers, we'll still have our 8 points. With 1 correct answer, we'll have 11 points. And we can go to the right, we can go to the left. I could change the window a little bit so we could see all of the points that we have on the graph. We want to make sure that the students now are making connections between the table and the graph. What do we want students to notice specifically about the graph? There are 2 primary points for students to see and understand. First, the graph is increasing. This is a little more substantive than what we might realize. As we read from left to right, the number of questions we answer is increasing. As we read from low to high on the graph, the number of total points is increasing. The 2 increasing directions, from left to right and from low to high, are important for students to see. Typically, they think only that the graph is going up, but we want them to see that as the number of questions answered correctly increases, the number of total points also increases. The second point is that all of these points fall on a straight line. Obviously, we're sowing additional seeds when we expect students to determine that this occurs because for each additional correct answer, we always receive the same additional number of points. That is, for each correct answer, we get 3 more points. Another correct answer, we go up 3 more points. Only after we're confident that students have mastered the numerical, the tabular, and graphical representations should we embark on representing our situation algebraically. Before leading students to a method that will help them identify an expression that will connect the number of questions answered correctly and the total points, students should be given an opportunity to explore on their own. However, they need to know what they're trying to do. To prepare them, students should be asked to predict how many total points would be earned for various correct answers, such as 20, or 15, or eventually x. In other words, don't stop until you reach a variable. Our main concern at this point is that students come up with an expression that determines the total number of points for any number of correct answers. We'll call our efforts define that graph. I'll exit from the trace with Shift F1. From the scatter plot, I'll select F2, define graph. Allow a student to predict what the expression might be. Suppose the student says 8x, as we've seen students do. Show them how to enter 8x in for Y1, 8x, with the execute key, and select F6, draw. Once they realize that if their expression is correct, the graph will go through all of the points, then they can have an opportunity to just muck around for a while, trying to come up with a correct expression. You might choose to do the very first problem as a whole class investigation. Encourage them to try to determine how changing their expression changes their graph. For example, students might try 3x. I'll go to define graph and I'll change this to 3x and draw it. They should notice that the angle, the slope, is now correct, but the graph doesn't go through the points. What might they do to adjust? Perhaps with some additional prompting, although we've seen 6th graders who don't need the additional prompting, students should discover for themselves that by adding values, they will raise the graph. And by raising it by 8 points, they will match the scatter plot. I'll go back to define graph. See what happens when I add 8 points. Draw it again. And this time we see the line going through our points. We encourage teachers to come up with multiple examples similar to this, using different contexts. Students, too, should be able to develop examples and challenge each other to define that graph. These initial relationships should focus on increasing graphs based on arithmetic sequences, which will always, of course, produce collinear points. Before moving on to decreasing graphs, it's time for some analysis. Our next goal is to derive the expression that connects our two variables by analyzing the numerical relationship. If you're viewing the graph, as I am, press Exit to return to the data. Though we wouldn't focus initially on this vocabulary, what we want to do is move from our recursive view of the total points in list 2, which we obtained by adding 3 points to each value, to an explicit one. Move the cursor to highlight list 3. Select Options, F1 for List, and F6 twice for additional choices. Select F5, which should now indicate Delta List. That triangle is the delta symbol. Type in list 2 to indicate we want to delta list 2 and press Execute. Delta refers to change. The first value, this 3 up here, indicates the change from the first to the second value in list 2. The second 3 indicates the change from the second value in list 2 to the third value, and so on. Obviously, every number in list 3 is 3, telling us the values are always changing by 3. How does this help us develop the expression we want? The expression we are seeking is, in essence, a formula that connects any value in list 1 to its corresponding value in list 2. Let's take a look. To go from 8 to 11, we have to add 3. To go from our starting point of 8 to 14, we have to add 2 3s. To go from 8 to 17, we have to add 3 3s, and so on. So how many 3s do we add? If we answer one question correctly, we had to add 1 3. When we answer 2 questions correctly, we have to add 2 3s. If we answer 3 questions correctly, we add 3 3s. If we answer 10 questions correctly, we add 10 3s. Eventually, we want students to understand that if we answer X questions correctly, then we add X 3s. In other words, we can start with 8 and add X times 3. We can write the expression as 8 plus X times 3 or 8 plus 3X. This delta list on the calculator greatly facilitates this type of analysis. When we have our graph and we define our graph, students might find it more natural to do 8 plus 3x. That's actually the form that I prefer to teach in, a plus bx, rather than ax plus b or mx plus c, especially for middle school students. All right. Let's try a similar problem, but one that decreases instead of increases. Suppose we're on a biking trip and we have 60 miles remaining on our trip back home. Further, suppose we're traveling 12 miles per hour. This time we want to explore the relationship between the hours traveled and the distance left. So I'll change this to hours, and I'll change this to left for the distance left. Students should readily be able to create the table of values in their lists. In list 1, we again begin with 0 and count the hours, so I'm going to leave what's there at least for now. In list 2, we input the distance remaining, which consists of 60, 48, 36, 24, 12, and 0. I'm just over typing. I could have deleted it. With students, I probably would have deleted it first. Students should see that we can stop counting the hours after 5, so I'll delete this value that's left here in my table in list 2, and I'll delete the 6 hours from list 1 and return to the home screen. Our graph is already set up for us, so we can simply draw graph 1. So I'll press F1 for graph and F1 again for graph 1. Students may take some time coming up with the correct function as they try to define that graph. Depending on how many experiences they have had, they actually might find it easier to define the graph by analyzing rather than exploring at this point. If so, this means we're making great progress in helping them understand expressions. Let's review the process. Return to the list with exit. And let's delta list 2 as we did earlier. To avoid potential confusion, this time I'll delete list 3. And then I'll highlight list 3 and select Options, F1 for list, F6 twice for additional choices, F5 for delta list, and I'll type in 2 to indicate that we want to show the changes for list 2 and press Execute. This time the changes are all negative, specifically negative 12. How does that help us derive the correct expression or formula? After 1 hour, we'll have 60 minus 12 miles left. After 2 hours, we'll have 60 minus 12 minus 12, or 60 minus 12 times 2 miles left to go. After 3 hours, we'll have 60 minus 12 minus 12 minus 12, or 60 minus 12 times 3 miles left. We hope by this point that students have a sufficient understanding of variables to determine that after X hours, we'll have 60 minus 12 times X miles left. However, keep in mind this may require many similar explorations until the students are ready to do this on their own. If we return to the scatter plot, Shift Exit for quit, F1 for graph, F1 for graph 1, and try to define that graph, I'll press F2, by inputting 60 minus 12x, skipping the multiplication symbol, and drawing that graph, we should find that we have matched it exactly. Let me pause for a moment and check with John. John, are there any questions that are left outstanding at this point, or should I go on ahead?
The only question that was asked, Bob, was that in this second scatter plot, the grid lines did not appear, and I thought the reason for that probably was that the Y scale was a bit too small and would have cluttered that up. But if we went into View Window and made Y scale larger, is that correct?
Well, let's do it. Let's change that Y scale to, say, 12, since we're going 12 miles each hour, and redraw the graph, and there you go. So that was exactly it. Yeah, the calculator is programmed so it will only show grid lines if there are not too many of them.
Okay, very good. Thank you for that quick demo, and no other questions at this point.
Okay. Well, let's now extend our work with expressions and build toward a deeper understanding of equations, or perhaps an introductory view of equations. We'll return to our original scenario in which we have 8 points and receive an additional 3 points for each correct answer. So here we had questions, and here we had total points. And this time, I'm to try to avoid confusion later on. Let me come here and delete list 3 so we're not confused by that. Although I still have to change the values in list 2. I hope that's not too confusing. I could delete them. In list 1, I'm going to include a few other values. I'm going to include 6, 7, and 8. Let me go ahead and delete the values in list 2 just in case anybody gets a little confused, and I can put the label in there later on. What I want to do this time is to take a shortcut to recreate the values that we want in list 2. But this shortcut is one that's going to reinforce students' growing understanding of expressions. Recall our formula is 8 plus 3x. We just have one more realization to make, namely that our x values are those values contained in list 1. We'll highlight list 2, which I've already done, and press 8, the addition symbol, 3, the multiplication symbol if I choose, Shift 1 for list, and 1 to identify list 1, which again, list 1 contains our x values. When I press execute, our list will be recreated for us. Might seem like a simple thing, but notice how we're reinforcing students' understanding of algebraic expressions. I'll re-put the label in here of total. Our original problem was to determine how many questions we need to obtain 20 points. Before taking on the approach that I'm about to describe, which is for those with previous work solving equations in a single variable, I strongly encourage teachers to give students many experiences using concrete models, such as those available through something like hands-on equations, along with their intuitions, which we can guide through our questioning to develop students' facility in solving equations. For many weeks, algebra should be used to record what students have, not as the means to solve the equations. Let me return to the PowerPoint for a few minutes to try to show you the types of questions we might ask. particularly after some experiences with concrete models such as hands-on equations, students should be able to now use their intuitions to answer these questions, and they're just using algebra to express their answers symbolically. How can we express that the total number of points we seek is 20? Well, students should be able to come up with 8 plus 3x, that's our total number of points, and that's supposed to be 20. The algebra is just to record their intuition. We're not going to use this to solve it. The algebra is actually just recording of what we have. The next question we might ask is, how many additional points do we need, and how can we express that? Well, of course, the additional points we need is 12, and 3x is representing the additional number of points that we're going to get. So we can express that as 3x equals 12. We then might ask, so how many questions must we answer, and how can we express that? Well, to get the 12 points, students can use their intuition to say, well, we've got to answer 4 more questions. Again, after using concrete models and then developing their common sense, we can help students develop and then own most of the rules essential for solving at least linear equations. Once this foundation has been set in place, then the calculator can be used to expand students' views of equations and what the solutions really mean. Rather than viewing the equal sign as meaning something like, and the answer is, an idea that unfortunately students often develop in elementary school, the approach we present here emphasizes that the equal sign indicates that 2 different expressions are perfectly in balance. Once students have developed these understandings, the calculator can significantly deepen their knowledge of equations. Let's go to the graph menu on the calculator. So menu, and I'll go to the graph. And what I want to do is delete what's there so I can start something over. We are trying to determine where 8 plus 3x equals 20. In other words, when did the 2 expressions, 8 plus 3x and 20, have the same value? In y1, I'll enter 8 plus 3x. In y2, I'll enter 20. Though it is typically good for students to determine an appropriate window, I'm going to set it now using values that I liked after I did some exploring. I'll press Shift F3 for the viewing window. I'll set the X min at -1, the X max at 8, the X scale at 1, which it already is, the Y min at -5, the Y max at 22, and the Y scale at 3, because each problem gets us 3 additional points. I'll press Exit to leave the viewing window and F6 to draw the graph. Here the Y value of each point on the blue line represents the total number of points. It increases by 3 for each additional correct answer. Y is the red line horizontal. It represents 20 points and does not change. The Y value for this one is always 20, no matter what our X value is. How can we solve the equation from this graph? We simply want to find when both expressions have the same value. That is, we want to find their intersection. Select Shift F5. The shift isn't necessary when we're looking at the graph. And select F5 for intersection. We see that the graphs intersect when the number of additional questions answered, the X value, is 4, and the total number of points, the Y value, is 20. Something that may shed some additional light on the process of solving equations, including for many teachers with whom we have worked, is to solve graphically at each of our algebraic steps. Recall that after beginning with 8 plus 3x equals 20, our next step suggested that 3x equals 12. I'll exit from the graph. I'm going to deselect y1 and y2. And I'm going to enter 3x for y3 and 12 for y4. And I'll draw this graph. Let's find the intersection. I'll use F5 and F5 again. Again, we see that the graphs intersect with 4 additional correct answers. But what does the 12 indicate this time? Our prompt for getting to this step was to ask how many additional points we needed beyond the 8 to reach 20. Therefore, the 12 here indicates that 4 correct answers will produce 12 more points. After we found the 3x equals 12, we then asked how many questions we would need to obtain these 12 additional points. It is, of course, 4, so our last step indicated that x equals 4. Let's look graphically. I'll press exit to leave the graph. I'll deselect y3 and y4. I'll enter x for y5 and 4 for y6. And I'll draw the graphs. Once again, we'll find the intersection, F5 and F5 again. Once again, the x value is 4, but this time we're saying that this x value of 4 indicates we need to answer 4 additional questions correctly. Let's now exit and have all 6 graphs selected. So I'll reselect y1, y2, y3, and y4. And I'll draw the graphs. Try to view the graphs as 3 pairs of lines. The blue and the red one, the green and the magenta, and the black and the blue. Though there are other intersections, let's find again the intersections of y1 and y2, y3 and y4, and y5 and y6. Select F5 for GSolve and F5 for intersection. With y1 highlighted, I'll press execute. y2 is now highlighted, and I'll press execute again. And I'll press execute one more time so the coordinates remain on the screen. I'll repeat this process for the intersection of y3 and y4. GSolve, intersection. I'll down arrow till y3 is highlighted. Press execute. With y4 highlighted, I'll press execute again and execute once more so the coordinates appear on the screen. I'll go to GSolve and intersection. I'll arrow down till y5 is selected. Press execute. With y6 selected, I'll press execute again and execute once more. Now this is a pretty sophisticated approach to equations and one for more advanced students, but I think it's pretty helpful. We're transforming the equation each time from 8 plus 3x equals 20 to 3x equals 12 to x equals 4, but we're doing this without changing the x value of the solution. We've encountered many teachers who believe that solving equations graphically is in essence cheating. Though we certainly want and expect all of our students to learn to solve linear equations in one variable, systems of linear equations, quadratic equations, and some other types of equations algebraically, that is through symbolic manipulation. When we consider the big picture, we should realize that we have very few types of equations for which we have algebraic algorithms, that we are quite limited in the types of problems we can solve. In fact, most technological solutions do not use the algebraic algorithms that dominate our mathematics classrooms, but instead use other, more powerful methods, one of which is through graphs. Again, we do believe that students should be able to solve equations symbolically. However, we also believe that they should be able to solve equations for which they do not have algebraic algorithms. Let me return to the PowerPoint just for a moment to think about a different context, one that does not produce a linear relationship. Consider this scenario. Suppose there are 3,000 bacteria and they're doubling every hour. Rather than looking at a closed-ended question, we want to explore first. We'll look at the expressions and then move on to solving equations. I'm going to return to the calculator now. And as we did earlier, let's create a table of values. So I'm going to go to the menu and I'm going to go to statistics. This time Y1, we can keep the same numbers, but I'm going to call it hours. And Y2 is going to be the number of bacteria, or I'm sorry, list 2 will have the number of bacteria. Now I'm going to use list 2 measured in thousands. So rather than writing 3 with 0, 0, 0, I'll just put 3 to represent 3,000. And it doubles, and then it doubles, and then it doubles, and then it doubles, and then it doubles. And though I would like students to be able to do this mentally, I will point out that students can also use their calculator to do the arithmetic. They could just do 2 times 96 and let the calculator do the doubling that way if they choose to do that. So 2 times 192 and 2 times 384. Might have a few more values than we want, but we've got a bunch there. Our scatter plot is still set up for us, so let's take a look. Graph and graph. No grid because of the scaling that we've got going on here. Here we again want students to recognize, that the graph increases. As time passes, the number of bacteria increase. But this time the relationship is not linear. It's what we call concave upwards. This is to say that more bacteria are created in later hours than were created in earlier hours. It goes up higher here than it did over here, for example. If we return to the list and use our delta feature, so let me hit exit, go over to list 3, options, F1 for list, F6 twice, and there's our delta list under F5, and we'll delta list 2. We notice that we do not get a constant value as we did when we had an arithmetic sequence in the earlier examples. In fact, we obtain the same values as in our original list. If we keep delta-ing our deltas, if I went to list 4 and deltaed list 3, we'd never get a constant. The values will always form this same geometric sequence. Whenever we delta a geometric sequence, which means there is a constant ratio between terms, as we have here with a ratio of 1 to 2 between successive terms. 3 to 6 is 1 to 2, 6 to 12 is 1 to 2, and so on. When we delta that, we always get a geometric sequence. Though the values don't always match the original numbers as they do here. Though we're going beyond the purpose of our webinar, I'll mention this is because the derivative of an exponential function is exponential. While for our earlier scenario, when we had an arithmetic sequence, the derivative of a linear function is a constant. But I digress. I tend to do that. Even without a constant value for delta, we can still develop the expression we seek, especially if students have had lots of experience with arithmetic sequences and linear functions. We'll now work on this geometric sequence, which leads to an exponential function. In 1 hour, there will be 3 times 2,000 bacteria. In 2 hours, there will be 3 times 2 times 2, or 3 times 2 to the second power, 1,000 bacteria. In 3 hours, there will be 3 times 2 times 2 times 2, or 3 times 2 to the third 1,000 bacteria. In 4 hours, there will be 3 times 2 times 2 times 2 times 2, or 3 times 2 to the fourth 1,000 bacteria. Though I'm going far more quickly than I would with students, in X hours, there will be 3 times 2 to the X 1,000 bacteria. Let's look at the scatter plot. So Shift exit to quit, graph, and F1 again for graph 1. And let's again play define that graph. So I'll press F2. We have analyzed the sequence and we have determined that we think the expression for the number of bacteria measured in thousands in X hours is 3 times 2 to the X. I'll input that into Y1. 3 times 2 raised to the X power. I'll make sure that's our only selected function. Notice the others are deselected at this point. So our only function that we have right now is 3 times 2 to the X. When we draw the graph again, we see that this does go through all of our data points. We have played define that graph correctly. Let's now consider some related questions that we might ask involving equations. If Y1 represents the number of bacteria in thousands, then our expression becomes part of an equation, specifically that Y1 equals 3 times 2 to the X. When we're working with this equation, if we know the X value, we don't need any fancy algebraic techniques to determine how many bacteria there are. For example, we can determine how many bacteria there will be in 2.5 hours by substituting 2.5 in for X into our expression. Certainly we would want to use a calculator to perform the arithmetic, but there's no major leap in understanding and no significant algebra required. We'll simply go to the Run Matrix menu and then 1 for Run Matrix. Input 3 times 2 raised to the, and I'm going to just input 2.5 for 2.5 to save a little bit there. When I hit form to decimal, we'll see that there's about 16.971 thousandths, or about 16,971, somewhere in there. That's the number of bacteria. But what happens if we want to determine how many hours it will take until we have 150,000 bacteria? Until students have studied and learned logarithms, they have no algebraic technique which will allow them to determine the answer. Nevertheless, I would expect students to be able to answer this question. We're asking students to solve the equation 150 equals 3 times 2 to the X. We could return to the statistics menu to get an estimate from our table. So menu statistics, and where would it be 150? Well, we can see that it's sometime between 5 and 6 hours. But we want something more precise. Let's move over to the graph menu. So menu and number 5 for graph. And let me delete these others that are here to try not to clog up the screen too much. I could just deselect them. And I'll select this first one. And for Y2, I'll plug in the value that we're looking for, which is 150. I'll draw the graph, and as before, we'll find the intersection, GSolve and intersection. What we see is that in about 5.64 hours, there will be 150,000 bacteria. An alternate approach for solving an equation of this form would be to draw only y sub 1. Let me deselect y sub 2. Go to F5 GSolve, F6 for more options, and do an X calculate and type in 150 for y. And again, we come up with the same answer. By taking advantage of the graphing calculator, students can solve problems like this despite a lack of algebraic techniques available to them. I would argue that this is every bit as powerful as having them solve the same problem after they have learned logarithms. In fact, I would argue that this technique is even more powerful, as often it is not merely a matter that students have not yet mastered an algebraic technique, but that no algebraic technique even exists. The calculator opens up avenues for exploration and greater understanding than is achieved in the typical non-technology mathematics classroom. I hope you've enjoyed this webinar and that it's provided you with ideas of how to foster algebraic thinking by progressing from context and the acting out of scenarios to concrete models to numerical and visual representations, and finally to abstract representations using variables and other symbols. Until students have had the appropriate experiences that promote abstract thinking, the ideas that may seem obvious and intuitive to us remain obscure or hidden from them. This is a primary cause of the lack of understanding and appreciation of mathematics that permeates our society. Rather than viewing mathematics as sense-making and as a means to help interpret the world around them, students are forced to memorize mathematical techniques and algorithms with little understanding of what it all means. No major epiphany will occur without these needed experiences, and it is our obligation as teachers to provide these opportunities for students. The PRISM provides a powerful tool for facilitating these experiences, allowing students to progress as they become abstract thinkers. We encourage you to read and then engage your students in the many investigations involving expressions and equations that are contained in the book, Fostering Mathematical Thinking in the Middle Grades. As the fundamentals of algebraic thinking that I try to address here, those that are addressed in the book are essential for later success in higher level mathematics. We also encourage you to attend other webinars sponsored by Casio as we all strive to make the mathematics classroom relevant, interesting, and thought-provoking. For more information, please visit www.casioeducation.com, www.casioeducation.com/prism, and www.casioeducation.com/support/educators/webinars. Before we say goodnight, let me check with John to see if there are any questions that I didn't answer in my talk. John, we got anything else?
No, Bob. We are good with the questions. Certainly your expertise on how young people learn mathematics is extraordinary. So we thank you very much for sharing that with us tonight. And again, to people that had the good fortune to listen in tonight, may I also encourage, tell your friends that this webinar has indeed been recorded. And as Bob's screen showing here, we can go to the CasioEducation.com website and listen to this one or many of the other quality webinars that are available there. So thank you so much, Bob.
Thank you, and thank you to all who were there. Thanks for your participation.
All right, good night, everybody.
Good night.